This article is The Mental Rotation of Facial Profiles, Age, Sex, and Ability-Related Differences by Merriman, List, and Keating. The goal of this study is to examine age, sex, and ability-related differences in processing underlying mental rotation of facial profiles. Studies of Cochrane, Pick, and Pick showed that for adults, the latency to determine if facial profiles presented in succession are identical or mirror reverse is a linear function of rotational disparity, indicating that adults can apply a mental rotation strategy to facial profiles. The purpose of this study was to extend the findings to a younger age group. Carey in 1981 provided evidence that there is a plateau or slight decline from 10 to 14 years of age, followed by an increase from 14 years to adulthood in the ability to recognize and match pictures of faces. Review of previous research on age, sex, and ability-related differences in the speed and accuracy of processes underlying mental rotation found that two process measures have been investigated. Slope of the linear function relating reaction time to rotational disparity, which is the rate of mental rotation, and the intercept of this function, which is the measure of the combined rates of encoding, comparison, and response. Developmental studies found declines in intercept with increasing age, but have not produced consistent findings about slope or error. There is evidence for developmentally sensitive sex-related differences in spatial ability. Research on adults showed that the average rates of mental rotation of women is 75% as fast as those of men. The results suggest that in at least one of the processes of encoding, comparison, and motor response accounts for a small portion of differences in general spatial ability. For ability-related differences, a correlation of approximately -0.3 between intercept and spatial ability test performance has been found. Findings concerning the relation between the rate of mental rotation and spatial ability have been inconsistent. According to Lohman's analysis of several factor analytic studies of spatial ability, the distinction between spatial relations and spatial visualization factors reflects two complementary dimensions of test performance: simple versus complex processing and speed versus power. Speed of mental rotation may not predict performance on spatial visualization tests because speed is not a limiting factor on these tests, and/or because other variables such as insight or logical ability are more significant predictors. The relation between rotation rate and spatial ability may be sensitive to sex. Asymmetry has been found between male and female subjects on some rotation rate spatial test score correlations. There have been few attempts to assess the relation between error in mental rotation tests and performance in spatial ability tests. The present study examined age times sex effects in the processing parameter correlates of spatial ability. Method. The subjects were 144 right-handed subjects, 48 were adults enrolled in a child psychology course at the University of Minnesota, 48 were 8th graders from the Minneapolis Public Junior High, and 48 were 4th graders from the same district, and there are equal number of sex in each group. The stimuli were constructed by combining elements from 5 sets of different facial features: hairstyles, eyes, noses, mouths, or chins. 4 faces were constructed as seen on the right in Figure 1. Slides were made of the 4 profiles in 6 orientations: upright and rotate clockwise 60, 120, 180, 240, and 300 degrees. Copies were made of the slides and flipped about their vertical axis to yield mirror images and were used for the rotated faces task. All subjects were given Raven's standard progressive matrices and the Woodcock-Johnson picture vocabulary and spatial ability subtests. In addition to the other 2 tests, the adults were also administered the card rotation, cube comparison, and advanced vocabulary 1 subtest of the ETS, the Educational Testing Service, kit of cognitive factors. And the Woodcock-Johnson test was designed to assess both spatial relations and spatial visualization factors. Procedure. All tests were given according to standard instructions, which is 3 minutes per section, except the 4th graders card rotation subset, which was increased to 6 minutes per section. And except for the Woodcock-Johnson subtest, all tests were administered to groups. The slides were presented on a rear projection screen. On a table in front of each subject was a console with 2 push buttons. The button on the right was labeled normal, and then the left button was labeled backward. Before the task began, subjects were shown a card with a line drawing of an upright right-oriented face. The subjects were instructed to push the button on the right with their right hand if a profile that faced to the right appeared on the screen. They were told that this was a normal face. The subjects were then shown a card with a line drawing of an upright left-oriented face. They were instructed to push the button on the left with their left hand if a profile that looked to the left appeared on the screen. They were told this was a backward face. Subjects were shown 3 or 4 cards with line drawings of rotated faces and were asked to indicate by pushing an appropriate button whether the faces would be normal or backward if they were rotated to upright positions. And then, after getting a certain number of these correct, the actual experiment began, and the experimenter recorded the subject's errors and response times for all slides. In addition to the psychometric scores, there were 5 dependent measures: median reaction time, R-squared, slope, intercept, and error rate. In all designs, age and sex were between subject factors, and all other factors were within subject. Results of the processing parameters. The first 24 trials of the rotate face task were considered practice trials and were not included in any of the latency or error analysis. The median response latency was chosen as the measure of central tendency for this experiment. And age by sex by degrees of rotation by response ANOVA indicates significant effects for age, degrees of rotation, and response. There was a significant age by degrees of rotation interaction and a sex by degrees of rotation interaction, indicating that the pattern of response latencies differed due to both age and sex. There was a difference between the pattern of normal and the pattern of background response latencies for each age group. The values for 120 degrees rotation were much higher than those for 240 degree rotation for normal, but the opposite was found true for the reverse. A second ANOVA was performed with degrees of rotation recorded as degrees rotated in the degrees of profile face. For example, 300 degrees and 60 degrees both became recorded as 60 degrees. This ANOVA yielded almost the same results as the first, with the exception that the age by degrees of rotation by response type interaction was not significant. Figure 2 on the right indicates that the curve from 0 to 180 degrees and the curve from 180 to 360 degrees in each age times sex group are not perfectly linear. One disturbing feature of the latency data is that 9 out of 12 inclines or declines are not monotonically increasing from 0 to 180 degrees. The post-hoc explanation is that many older subjects did not mentally rotate profiles to 0, but a position between 300 and 330 degrees. And the reason this occurred is because the hairline, eye, and nose all lie in the upper half of the visual field while rotating to between 300 and 330, and therefore more errors were made to the upright faces than those rotated 300 degrees. For the remaining analysis, both models were used. An age by sex ANOVA of slopes revealed only a significant effect for age and sex, and an age by sex ANOVA of intercepts revealed only a significant effect for age. Error analysis. The overall error rates of each age by sex group were low. An ANOVA of error rates revealed significant effects for age, degrees of rotation, and degrees of rotation times response type. No other effects were significant. The age group mean error rates were 3.5% for adults, 5.3% for 14-year-olds, and 4.4% for the 9.5-year-olds. Table 2 displays group means for all psychometric tests. Of the 3 tests given to all age groups, an age by sex ANOVA showed significant sex effect for both of the Woodcock-Johnson subtests, a significant age by sex interaction for Raven matrices, and an age by sex interaction for the Woodcock-Johnson spatial subtest. The age by sex interactions reflects the tendency for the direction of sex-related differences in 14-year-olds to differ from that in the other 2 age groups. Now this is the look at the means for all psychometric tests. Correlational analysis. Slope, which is the rate of mental rotation, and intercept, the rate of encoding comparison response, error rate, and several psychometric tests were examined for their interrelations with the total sample, each sex, each age group, and each age by sex group. Striking sex-related differences were found in many of the processing parameter test score correlations within age groups. In the adult sample, there are 3 interesting results. The correlation between mental rotation and test performance was non-significant. There was a substantial correlation between intercept and spatial relations test performance in male subjects, and there was a substantial correlation between error rate and both spatial and vocabulary test performance in the female subjects only. In the 14-year-old sample, no significant parameter test correlations were found except between error rate and spatial test performance, and in the 9.5-year-old group, the rate of mental rotation was significantly correlated with every test score. The results of the study replicated the finding of Cochran et al.'s 1983 finding that adults use a strategy of mental rotation to determine whether a rotated facial profile would face left or right in the upright position. The present study extended the findings to 9.5 and 14-year-olds and also found that many of the older subjects mentally rotate a profile to a position in which the profile is tilted 30 to 60 backwards rather than upright. The vertical symmetry of upright facial profiles appears to present problems only under single-item presentation conditions. Age-related differences. The results of the study support the hypothesis that there is a developmental increase in both rate of mental rotation and the combined rate of encoding comparison and response from middle childhood to young adulthood. The greatest change takes place between 9.5 and 14 years of age, but changes might also occur after 14. The study also found a developmental patterns of error in rotating facial profiles that is similar to the pattern of error that Carey observed in face recognition and matching. Sex-related differences. Mean rate of mental rotation was faster in males and females in every age group. The variability of female rates of mental rotation was approximately 50% greater than male rates at every age, suggesting that only a portion of females have a slow rate of mental rotation. Ability-related differences. There is a parallel between the developmental decline observed in the two latency parameters and the developmental increase observed in test scores. Some of the developmental increase in test performance is due to an increase in the speed of specific processes. The finding of a non-significant relation between rate of mental rotation and test performance in adults can be explained by there not being a general relation between rate of mental rotation and spatial ability, but there are relations between rates of mental rotation of certain contents on certain spatial tests. This means that knowing an adult's rate of mental rotation will not predict his or her general spatial ability. Conclusions. The discrepancies concerning the change in mental rotation rate from middle childhood to early adulthood are most likely resolvable in terms of speed-accuracy trade-offs. The relations between processing parameters from the mental rotation task and the ability test scores were not general, but were sensitive to age, sex, and differences between test scores within the spatial ability domain.